Okay, so hello everybody, and hello to everybody who's actually back at work. This looks like an exciting new development. This week we're very happy to have David talking to us about Axiverse dark matter. So David.
All right. So today I'll be telling you about dark matter in the Axiverse, and so to give a quick summary of what this is about. I think we're all used to thinking about axion-like particles as single particles with a single instanton potential, so just in a cosine potential. What we do in this project is we think about the Axiverse slightly more holistically, in that we're taking into account the fact that axions in the Axiverse not only have multiple instantons contributing to their potentials, but they also couple to other axions. And this leads to non-trivial dynamics that can have huge implications for direct detection and indirect detection today. Okay, so with that said, let's get right into it. So axions exist in many well-motivated extensions of the standard model. Notably, you have the QCD axion, which is hypothesized to resolve the strong CP problem. Now, the QCD axion acquires its mass through strong instantons, and the VEV of its potential exactly cancels the CP violating phase of the strong sector, resolving the strong CP problem. String axions, on the other hand, acquire their mass through string instantons, and they correspond to the many ways to wind around the 7 compactified extra dimensions of string theory. And generically, you expect many string axions, and this is because there are many independent ways to wind around a 7-dimensional manifold. Okay. So axions are natural dark matter candidates, and there are several ways to produce them in the early universe. The one that we will be thinking about is the misalignment mechanism. So broadly speaking, the way this works is that after inflation, the axion acquires some non-zero expectation value displaced from its vacuum expectation value. This means that the axion field has some initial potential energy that when the expansion of the universe slows down, such that the Hubble parameter is smaller than the mass of the axion, this initial potential energy gets converted into energy that dilutes like dark matter. The usual setting for this to take place is a single instanton potential with an instanton scale lambda for the axion field phi with a decay constant f. Here n is a domain wall number, which in this plot below I've taken to be 1, but it's important to know that n is a domain wall number for later. So the usual way this takes place is that the axion starts out some way away from here, and when the Hubble parameter drops below m, it begins to roll. So looks something like this. Hopefully the movie is playing relatively smoothly. Very quickly, it gets diluted to the bottom of the potential, where interactions are basically non-existent. At the bottom, the potential is basically quadratic, and you get dark matter, but not much else. If, however, the axion starts at the very top of its potential, then it takes a long time for it to begin rolling because the top of the potential is flat. This delay in oscillations means that by the time it does begin rolling, Hubble friction is much smaller than if it had begun rolling immediately. The fact that it's undergoing nearly undamped oscillations means that its oscillations will be larger amplitude for longer, meaning that it's probing the non-quadratic part of the potential. The non-quadratic potential, of course, corresponds to the interacting part of the potential, which corresponds to many-to-one processes, turning the non-relativistic fluctuations in the axion field into semi-relativistic modes that get parametrically resonantly enhanced, leading to density perturbations that seed small-scale structure. This includes axion mini-halos, which are just like the NFW profile of the galaxy, but on a much smaller scale. So this is a big part of galactic substructure. Boson stars, which are gravitationally bound like axion mini-halos, but supported by quantum pressure, and oscillons, which are bound together by self-interactions. Now, oscillons are semi-relativistic and radiate away their binding energy through many-to-one processes, and therefore they have a finite lifetime. But in the context of large misalignment, oscillons can have signatures because when they're produced and when they merge, they lead to the production of a gravitational wave background. And I mention oscillons in particular because in our model, they might not be restricted by these lifetime bounds. Okay, so let's just watch a movie of large misalignment. So pay close attention to the fact that the square has delayed oscillations and that its amplitude stays much larger for longer. Okay, so the circle gets diluted to the bottom very quickly. And now the largely misaligned axion begins rolling, and you can see it. It feels the self-interactions. Okay. So the key ingredient, again, for large misalignment is a delay in oscillations, making non-linearities in the potential accessible at late times, allowing for the parametric resonant growth of density perturbations. But what if instead of delaying oscillations, we simply put another interaction scale at a smaller, or another...
No, there's just one minor point that you have to shout. Can you hear?
Yeah, a little bit. I can hear Savas.
No, don't worry, then I won't.
No, I can hear.
Okay, so I didn't hear. So no, there's just another point that you stay longer at the maximum, so that so you remain with potential energy dominated longer, whereas
yeah,
the rest of the universe gets diluted, start diluting earlier. So
absolutely.
Density potentiality for density contrast.
Yeah, absolutely.
Density contrast. Anyway, that's part of the.
Wait, actually, can I ask one question?
Mm-hmm.
So, like, usually the axion is obviously not completely homogeneous throughout space, and I assume that usually happens like after many oscillations in various parts of space. You start, like, the phases go out of phase.
Yeah.
But if you're starting near the top and you want to stay like seeing the whole potential, I assume you can't go through too many oscillations between when you start rolling and now. So does that make the axion like much more homogeneous?
Sorry. So you're saying that because you stay at the top longer, I don't understand. I'm sorry.
Like between when this starts oscillating and now, has this gone through a lot of oscillations?
Oh, tons. Yeah. I mean, when you mean now, do you mean the present day?
Yeah, like today.
Oh, yeah. I mean, millions, billions.
So even if you put the ultralight axion, right, 10 to the minus 22 eV, that's like a year. Yeah. That's it here.
The delay is only like 10 oscillations or 20 oscillations or something.
Whereas
okay, but it still sees the whole potential, like even though it's gone many
today,
times.
it doesn't see the whole potential.
I see.
It's
Okay.
quadratic.
Initial evolution change.
But you oscillate no matter what. You always oscillate many,
Right.
taking some sizable number of times before the day, even
Okay.
for ultralight axion.
Okay, but when the non-linearities are important, you haven't oscillated too much at that point.
Depends on how fast the
I guess
axion
so.
is.
The longer you delay oscillations, the more time you can spend undergoing nearly harmonic oscillations exploring the nonlinearity. So, for example, if I delayed the oscillation until, like a million years ago, right, Hubble friction would basically not exist, and it would still be oscillating with this large amplitude.
Oh, okay. Interesting.
Yeah. So, okay. So this delay in oscillations makes the nonlinearities accessible, and that causes density perturbations to grow. But what if instead there are nonlinearities in the potential accessible at smaller energy scales? So that instead of waiting for Hubble friction to dilute by just hanging out at the top of the potential, we allow Hubble friction to run its course, but we now have non-trivial interactions at a much smaller scale. So the simplest example of a potential where this happens is a two-instanton potential. So we have, as before, the same lambda 4 single instanton potential for the axion phi with decay constant f. Added to it, however, is another instanton with scale suppressed by eta. Okay, so the fact that eta is small creates the separation in energy scales. And we have this extra domain wall number contributing, and a phase phi, or delta, excuse me. The phase delta does not play a significant role. So in these plots, I've taken it to be 0. You can easily take it to be not 0, and it doesn't change the physics very much. Okay, but when the domain wall number times this parameter eta are order 1, you get little wiggles in the potential that show up, okay? So the condition for interesting things to happen is that you have a separation between the instanton scales, and you have curvature scales of the potentials that are similar, okay? So what we're going to do is we're going to watch a movie of the large misalignment again, compared to some order 1 misalignment of this 2-instanton potential. And below, I've plotted a zoomed in version. So we can see how the physics of the 2-instanton potential at late times looks similar to large misalignment at late times. In particular, I want you to notice how it's spending a long time in this interacting part of the potential. Okay. So early on, it has a lot of kinetic energy, but after a short while, it dilutes. And now you can see that both the large misaligned axion and the 2-instanton axion are exploring the nonlinear part of the potential, undergoing nearly harmonic oscillations. Okay. So in general, you can get similar things showing up in multi-axion, multi-instanton potentials. And kind of the most general potential you could write down for n interacting axions is the following potential, where they have m instantons of scales lambda I coupled together through these charge matrices nij.
Thomas has a question.
Oh, yeah.
Oh, yeah, no, can you go back? So the moral of the story is that if you have a second axion like you've drawn, you can get a large misalignment for the effectively large misalignment for the low curve, for the smaller wiggle potential.
Exactly, exactly.
And yeah, it's not obvious because it could come with a kinetic energy that's so large that you don't spend a lot of time.
When the kinetic energy is very large, the ripples don't exist as far as you're concerned, right? The ripples take place on an energy scale. If the ripples are on a scale much smaller than the kinetic energy, the axion doesn't notice them.
Yes, but you're saying you will always, I'm just confused because it seems to me you could come down with large enough kinetic energy that you never see the ripples. You sort of go from large kinetic energy to settling at the minimum without feeling the ripples.
I fail to see how that's possible. I'm sorry.
Ending is a smooth process, so your amplitude will go through the regime.
Do that, and then you'll speak there.
Yeah, because when you spend a long time waiting, you get a significant delay.
Depends on data.
Yeah, yeah, of course. So if eta is, not significantly smaller than 1, say if it's not below like 0.2 or so, then it's possible to just end up in the minimum and never see the self-interaction, maybe.
But instead of saying that, do you require this n? I don't understand the n times eta has to be roughly 1, like that condition of the domain.
Basically, the condition that n times eta is order 1 is roughly like a visibility criterion for the scale of the wiggles. The wiggles are not big compared, or if the wiggles do not take place on with a similar curvature scale as the whole potential, then they basically don't matter. That's
it also means that both instantons give comparable masses to the axion.
Yeah.
So that's the requirement. Some approximate coincidence of scales.
Yeah. So yeah, it's a coincidence in mass scales, and this is a theme that shows up throughout any other potential we consider.
And if you don't have this, could you have a false vacuum or something? Could you have-
Absolutely. So you can have, if the ripples are too big, then you have false vacua, and you can get bubble production that can lead to gravitational wave signatures and so on. Yeah.
Is this coincidence finely tuned, or do you have?
No, it's order 1.
But I mean, is there some reason for this coincidence of
We
scales?
will get there. Yes.
Oh,
Okay. So in the Axiverse, you get similar things. Basically, that's the point of this slide. And for example, if you have 2 axions interacting through 2 instantons, you can get, for example, little wiggles in this theta s direction and large wiggles in this theta L direction, okay? And then if we let this axion, which is represented by a white ball, roll, at late times, it will see the wiggles in the theta s direction, okay? So we can watch that go. Okay, and now you can see that after, a significant amount of time compared to the mass scale, it's now wiggling with order 1 of the energy of one of these small wiggles. Okay, so basically this is, an argument that you get a lot of the same physics happening if you have this kind of separation of scales in the instantons and a coincidence in the masses. Okay. Now the justification for why you should expect this. So in the Axiverse, the instanton scale.
No, can you go back up? I just want to slowly observe this. So
You run the movie again?
Yeah.
no, I wasn't the movie part. No, I mean, this potential that you wrote seems extremely reasonable. Is it? Can you officially motivate? I mean, are there? I should ask you not now. Are there stringy papers that officially motivate this?
I mean, this is a rather detailed question that would require somebody
It's very
to.
reasonable. I just don't know. Maybe you could have written other things that also would be reasonable.
Yeah. I mean, I would not say that our search is exhaustive. It's.
But you found papers from wherever, Cornell, that motivate.
Yeah. So for example,
Separated Fs, for example.
Oh yeah.
Yeah,
Scales in general. Also lambda.
I'm sorry.
Here you get linear Fs in this dimension, right?
Yeah, it's M's that are typically very different. F's are more similar. Like it depends. David is going to give this slide, which talks about exactly.
Yeah, so I don't show the slide for the Fs, but the Fs can vary by a factor of 10 to 100 or so. Okay.
Most of these models.
10 to 100.
Yeah, Fs are relatively narrow.
10 to 100, 10 power 100. I was like,
He mentioned multiverse, but he didn't make use of that.
So no, the Fs can range by a factor of 10 to 100. Okay, which seems reasonable. I mean, yeah, we don't do realistic compactifications on our own, so we're anyway. But the rough justification for why you scan mass scales and why you should expect these order 1 coincidences in the mass scales comes from the fact that the axions acquire their mass through instantons that are exponentially suppressed relative to the UV scale by the string instanton action. And if you have order 1 variations in the string instanton action, then you expect the instantons to be log uniformly distributed. And roughly that translates over to the mass spectrum. In this case, the masses are log uniformly distributed. And you can see in this plot made by Virov, Mehta, Liam McAllister, and others, that you get roughly a log uniform distribution in some cases. If you're, I think what they say is if you're on the edge of the Kähler cone, you get these weird distributions, which we're not going to think about. In any case, if you have several axions per E-fold of
What's the edge of the Kähler cone? This is
I'm not asking.
engineering.
I'm just saying words. That's something that we should ask Virov or Liam.
Yeah, that's fine.
Yeah. Yeah, I had it explained to me at one point. I can't remember anymore. In any case, if you have several axions per e-fold of mass, you expect coincidences in the mass scale. Okay, and if you have coincidences, what this means is that the dynamical timescales of the axions are similar. We call these axions with similar mass scales friendly, and they can undergo nonlinear resonance together. Okay. So of course, scanning all possible realizations of the Axiverse is hard. So let's consider a simplified example of a multi-axion potential that exhibits non-trivial dynamics. So here we have the phi s axion and phi l axion, the small and large axions, that couple to each other through a single instanton here. And the large axion gets another contribution from this other instanton. The large and small labels roughly refer to the size of their respective decay constants. So here f sub s is suppressed relative to f sub l by the scale xi, which we take to be less than 1. This corresponds to the separation of instanton energies. Their masses are related by this parameter mu, which when it's greater than 1 means that the large axion has a larger mass. And the parameter mu roughly corresponds to the coincidence of mass scales. Okay, so just like before, you need a separation of energy scales and a coincidence of mass scales, and you get exactly this potential. Okay, so here you have this C suppression between the two wiggle sizes. And the fact that the small wiggles show up at all comes from the fact that mu is order 1. And in particular, we'll be interested in the case of mu less than 1. This is when we'll get nonlinear resonance. And in order to study this model in a particularly simple case, we go into the angular variables theta sub s and theta sub l. Okay. So in the limit of a large separation of energy scales between the instantons, xi goes to 0, we end up with the equation for a inhomogeneously driven pendulum. Okay, so the small axion looks like a driven pendulum. The large axion is just losing its energy density like dark matter because its energy scale is so much bigger. And if, for example, we did not have this sine term here, but it was just a linear oscillator, the resonance curve for the oscillator would just be this straight line, okay? In other words, the large axion could not transfer its energy to the small axion unless mu was equal to 1. The masses were exactly the same. But because we have a nonlinear interaction, the fundamental frequency of the pendulum depends on its amplitude. In other words, if the pendulum is oscillating with a larger amplitude, its fundamental frequency is smaller. Therefore, if mu is less than 1, you can have a nonlinear resonance with the driving term. Okay, so for example, if I were to drive this pendulum at half its fundamental frequency, that would correspond to an amplitude near pi. Okay. Now, in general, you might say that, oh, well, it's hard to lock on to this resonance. The answer is it's not. And this is a process called autoresonance. It is the process by which nonlinear oscillators lock on to a driving term and maintain a constant amplitude. So in order to see this, you can basically go and you can write down an effective potential for the relative phase of the driving term and the pendulum. And you see that it obeys the effective potential looks like this, okay? It's a cosine term plus a constant tilt. So I guess it looks like a relaxion potential kind of. And when this term is smaller than this term, you get stable minima. So something like this. And you can lie in one of these minima. So the condition for a stable evolution is this. And in this case, the amplitude and phase of the driven pendulum remain locked to the driver. Okay. The consequence of this is quite surprising.
Equation about this?
Yeah.
Equation. Do you have equation-free intuition about this?
Equation-free intuition about why they remain locked?
Yeah, it's locking.
So roughly, you can imagine that, so let's suppose that the driven pendulum is in equilibrium, okay? Its amplitude is constant and it's at the same frequency as the driver. Okay, now, of course, this means that you're dumping energy resonantly into the pendulum. Its amplitude increases, which means that its fundamental frequency decreases, and it is now off resonance, which means that you're dumping less energy into the driven pendulum. Okay?
It's a stable fixed point.
It's a stable fixed point.
On the swing, right?
Yeah,
You time your pushes to be exactly the right amount, and it will keep the kid at that point on the swing.
Okay.
So in practice, you don't stay at exactly the equilibrium. You get quasi-periodic oscillations corresponding to these, bouncing off of the resonance as you go along. So you can actually see that in this plot here. So you can see how
Friction brings you down. Yes.
friction also plays a role. Yes, friction brings you down as well. Yes. In fact, if it was not,
what decides how long you stay on this plateau?
back reaction. So when you can no longer think about theta sub L as being an independent driving force, now you fall off the resonance curve.
And when do you stop doing that?
So that's roughly when the energy density ratio has been flipped.
That's very
So yeah, so
Robert, did you have
so a little bit confused about here. So you're saying that you're treating the sigma L, the large axion thing, as a independent driving thing, even though its energy density is much smaller than the energy in the other
No.
one.
Okay. This is this is a simplified example when the energy density of the large axion is bigger.
Okay, but in the next one, you said that you carry on the model until it's much smaller.
Yeah. So the way to actually see that back reaction only kicks in at this when the energy density ratio is like this, you literally just compare the size of the terms in the equations of motion, and back reaction is actually additionally suppressed. So it's not when the energy densities are equal, it's when the energy density ratio.
Yeah, Robert, to be precise, the equations that David has on the previous slide are modified once you pass the point that that the energy density of the large mode drops below the energy density of the short mode, but very analogous equations hold until slightly later.
Okay, yeah, that sounds plausible. Thanks.
So, in other words, autoresonance is quite robust. If you get trapped, you stay trapped until you've basically sucked all of the energy out of the driving term. So, phrased in terms of astrophysical or cosmological consequences, if you started with two axions with order 1 misalignment and very different Fs, say the small axion has the black energy density and the large axion has the red energy density, if they were decoupled, you would expect them to follow these dotted lines. Okay, the axion with the smaller decay constant has the smaller energy density for all time. But because you get trapped by this autoresonance, the energy density of the small axion stays fixed until it sucked all of the energy density out of the large axion driver. And in this case, you subvert the expected energy density hierarchy. So if somebody were to detect this axion, they would be very surprised to find that it has such a small decay constant and is all the dark matter. Okay. So how tuned are these initial conditions that lead to the subversion of the expected energy density hierarchy? In order to answer this question, it's helpful to look at these plots. So
Savas is quoting the Bible at you.
Oh, yeah. What is it? What do you say?
The small shall inherit the earth, the meek.
Yes. Absolutely.
And they couple more strongly.
Yes. So the small axion, okay, so these plots represent the log of the ratio of the small energy density to the total energy density. So up here, that corresponds to the small axion dominating the energy density. Here, mu is, of course, the detuning. So when mu is less than 1, the driver is at a frequency smaller than the fundamental of the small axion. And these two plots correspond to F ratios of the order 0.1 and 0.01. Okay. And in order to make sense of these plots, you need to know that each vertical slice is a histogram over initial condition parameter space. So we sample uniformly the initial conditions of theta S and theta L range from 0 to 2 pi. And the darker the plot is, the more likely you are to end up with that final energy density ratio. Okay. So both plots exhibit the same features. And for small mu, you can see that you end up with the large axion dominating the energy density, the relic abundance. Same for large mu, bigger than 1. But for mu of order 0.7 to 1, you end up on this autoresonance. And in fact, order 1, if not most of the initial conditions, end up autoresonating. And you get this subversion of the expected energy density hierarchy. Okay.
And how do you think you'll explain how you understand?
The fraction of initial conditions?
Yes.
How do you, so you're asking, how do you explain?
Why is it not more tuned?
Why is it not more? So you're asking, which parameter are you asking about?
Oh, I don't know the name. Is it C or?
Oh, why can C be as large as 10 to the minus 1?
Say.
Sure. I mean, the only criterion for autoresonance is that you're exploring order 1 of the nonlinearity when the Hubble friction is not like forcing you to the bottom of the potential. So you need a big enough separation of energy scales that you can explore the small wiggles at when you're underdamped. But that's it. That's the only condition. Okay, sorry. Maybe we should talk about this later. Okay, so the answer is it's not very tuned. It requires an order 1 condition coincidence in the initial conditions. And the fact that you
there's also the coincidence of scales. There is also the coincidence of scales.
Yes, that's true. So you have 2 coincidences, but as we'll see, even the case when you don't end up on the autoresonance is still interesting. So, you know.
It's interesting. I just want to count. There is, let's say, I don't know, 20 orders of magnitude, tens of orders of magnitude between the high scales and low. So you would need, like 100 axions equally distributed would result into inevitable coincidences of scales.
Yeah.
Does this whole story hold if you have more than 2? So I understand if I can do 2 together, right? But say I have 10. Do all of the 10 have to be close to each other? Or can I have 2 and the other thing is somewhere else?
If 2 are here and very far away, it has no effect. There's no sort of nonlinear couplings between these guys.
But if
these similar dynamical timescales.
Or you mean 3 close by?
Yeah, if you have like 3 guys that are close in mass, we haven't investigated this in detail, but the
so I mean, that's the tuning. If you count the tuning by doing 2, does that necessarily carry over into, say, I have 10, right? Is it really just I can tune any pair of them and the others don't really have an influence, or does it really change the tuning?
This depends on how they're coupled, because of course, if I introduce another axion to, say, where is it? If I introduce, say, a third axion here that basically has no other potential, of course it ruins the interaction, right? So, you kind of rely on dense couplings in a sense. You need every axion to kind of have a non-trivial potential if they're interacting.
So is it a coincidence that the two axions that you're looking at, if you're in a 10 axion model, coupled to the same instanton? Like you have 10 axions, 2 of them that you're interested in coupled to the same instanton in that way.
If you expect that each axion couples to every other, maybe not through the same instanton, but at least there's one instanton coupling every axion to every other, then no.
I see, but in the model that you wrote down, you said that things would change if you had up to more axions that are also coupled to that same instanton, right?
I mean, this is a question that, I mean, at the end of the day, really requires, you know, a lot of math, I think. But if you were, I'm just making kind of the stupid point that if you put an axion in here that basically acted as like just some free phase with no inertia, it basically means that this instanton does nothing.
Okay.
Yeah, does that make sense? I'm just saying, like, you know, there is some condition that if your interaction is meaningless, like there's some axion in here that's doing nothing, then you know, then the interaction doesn't matter, and yeah. Does that kind of make sense?
Yes.
Okay.
Wait,
So,
I have perhaps naive question about this whole Axiverse story. Like so the point is basically you want to get like one axion to dump all its energy into another axion, and then that one will be the dark matter.
yeah.
But like in order to have this not be finely tuned, you have to have like hundreds of axions, which presumably all have their own energy density. Like what happens to those ones? Why do
Yeah,
I
so presumably you'd be most concerned with the axion with the largest decay constant that contains most of the energy density at early times.
So not only do you need to have these two axions that are close to each other in mass, but also it needs to be the one with the largest decay constant?
Well, no. The constraint that it's the largest decay constant is not a constraint. That's what you expect.
So sorry, this is already an issue in like talking about out dark matter in the Axiverse, right? Like all there, if they're just randomly distributed in X and M's, then they might be too much. They might overclose the universe. So you already rely on the fact, just whenever you're talking about like out dark matter, that you have one guy that happened to have roughly the right misalignment contribution. The new thing here is pointing out that if this guy, that one guy that you thought would have been the dark matter, has a friend that's nearby, then he can dump all of his energy into the friend, and the friend can have a much lower decay constant, which you would have never thought could have been misalignment produced. And so you see something that you never would have thought could have been the dark matter, but really it is because he was friends with the one guy who happened to be the right misalignment.
Okay, but so the story is not that amongst 100 you just need to have two friends. It's that one particular axion needs to have a friend amongst 100.
Yes, but if you have 20 orders of magnitude and you have 100 guys, then actually a lot of them are going to have friends.
Right.
Okay. Yeah, you're going to have a lot.
Hey, so just to ask a different question, if we're thinking about an abundance from strings, as well as if we're imagining that kind of scenario happening, then the abundance should scale with n, right?
The abundance.
The dark matter abundance you get. So in which case you'd have the large n and the small f would presumably give you an expected abundance, which is similar to the original, the larger f, smaller n one. So yeah, I guess in these scenarios, is the point that you always care, you don't expect any string contribution, you expect all the stuff to be misalignment?
Sorry, maybe I misunderstood. Say one more time, I'm sorry.
And also, well, I guess there's a question of if you ever have any string net which needs to worry about domain walls and things and whatever. So you're just assuming that you never actually form any defects. Is that the idea?
Oh, yeah. This is the simplest version of the story where you don't form defects, yeah.
So we're going to assume that all of the So inflation occurs at a small enough scale such that all the axions have F's above it and we don't form any defects.
Yeah.
Okay.
Yeah, exactly. Yeah. So that's the simplest version of the story, and that's the one we're focusing on. Yes. Okay. So sorry. Any more questions before we move on? Okay. So the fact that the small axion remains on this autoresonance for a prolonged period of time means that it's exploring order 1 of the nonlinearity of the potential for a prolonged period of time. And this is basically the condition for having parametric resonant growth of density perturbations. So in order to see how this compares to large misalignment, I've stolen one of their plots. So here we look at the relative density perturbation of co-moving wave number k versus the scale factor a. And here k tilde refers to rescaled co-moving wave number that's order 1 for wave numbers that are the axion wavelength at the time the axion begins rolling. In other words, you expect k tilde of order 1 where interesting things happen. So you can see on the left plot that you get, for small k tilde, cold dark matter predictions. For k tilde of order 1, you get early collapse of structures due to gravitational interactions. And for k tilde of order 3, you get quartic collapse during radiation domination, leading to oscillon production. For the 2-axion scenario, you get exactly the same picture. So you get cold dark matter prediction, early collapse of structures, and quartic collapse. The key difference is that in order to get this phenomena with large misalignment, you relied on a 10 to the minus 12 tuning. For the 2-axion scenario, you only required an order 1 coincidence. Okay. All right. So because you're being driven on this nonlinear resonance for such a long period of time, you have the potential to generate non-perturbative structure. And indeed, you can generate non-perturbative structure, or the density hierarchy flip can happen before, in which case the density perturbations will not be as big. And if you end up on the autoresonance, the outcome only depends on these 2 Lagrangian parameters, xi and mu. Roughly, the intuition for this plot comes from the fact that when xi is small, the separation of scales between the 2 instantons is large. And this means it takes longer to transfer all of the energy from this large axion to the small axion, which generates, which means that you have more time to generate density perturbations. As mu goes to 1, it becomes harder to generate density perturbations because the autoresonance takes place at a smaller amplitude. The detuning is smaller, which means that the autoresonance is at a smaller amplitude and the production of density perturbations is less efficient. So that roughly explains the shape of this curve. When we do the numerical experiment, we find that it actually is slightly above the theoretical expectation. And that's because prior to autoresonance, there's a period of transient large amplitude oscillations that also generates density perturbations. It only needs to change the initial density perturbation by a factor of a few in order to cause this boost in density perturbation growth. Okay. So finally, what about those initial conditions that don't autoresonate? So in this case, the small axion is a subcomponent, and the large axion, as you would have expected, is the dark matter. But because the large axion is still with a frequency that can support nonlinear structure in the small axion, if you form things like oscillons or solitons, they can be driven nonlinearly. And this means that even if the large axion has a decay constant that puts it out of reach of direct detection experiments, the small axion can have unsuppressed interactions with the standard model. In other words, oscillons have axion field of order F inside of them, and therefore they scatter with light with only an alpha suppression. Did you have a question? Okay. Okay. And with that said, in conclusion, the Axiverse scans many mass scales, and if you have enough axions, coincidences are almost inevitable. Coincident mass scales lead to resonances between axions with different instanton scales, and this can lead to perturbation growth in the early universe and a matter power spectrum that is boosted at smaller scales today. And surprisingly, you can get the axion with the smaller decay constant dominating the relic abundance of dark matter today. And even if that hierarchy flip does not occur, in that scenario, you can have oscillons that live parametrically longer than they would in vacuum because of autoresonance, leading to dramatic signatures today. And with that said, I'm going to plug the Art of Science competition, which one of our plots got selected for. So, you know, if you like what you see, show it by voting at this URL, where they have a virtual exhibition, and you know.
I think this URL technically isn't live yet, so
Yeah.
if you're about to go don't do it yet. Vote in a few days.
Yeah, exactly.
You
Anyway.
have to email the link around, no, because nobody's going to be able
Yeah,
to
we'll publicize that.
Yeah, and finally, just a poem to think about. Okay. With that, any questions?